Hey, welcome everyone. This is Control, and as usual, we're streaming. We've been streaming for around 29 years, for around a month, and as usual, today we're gonna solve some lead code problems. So the lead code problems for today, uh, we are using for the binary search tree. We're gonna practice some binary search tree problems, and the topic for today, for the ones every day or every data structure problem, we choose a topic, and the topic for today is Sherlock Holmes investigations. So we're gonna search the first problem. We're gonna help Sherlock track down a critical piece of evidence hidden within a well organized archive. And the second problem is the delete node in a binary search tree. So Holmes carefully removes false lead from the case while keeping the investigation intact. So without further ado, let's go to the lead code problem. But before that, don't forget to follow me on GitHub. Don't forget to follow me on my social media account. This is my LinkedIn, this is my GitHub, this is my Instagram, and recently we did a server Discord. You're free to join it. And without further ado, let's jump to the problem. So yesterday we did a BFS binary tree, and today is the search. So I'm gonna make it here. I'm gonna make it here, and let's remove this. Okay, let's remove that. And yeah, so now we're good. So let's go to the first problem. It is a search binary tree. This should be easy. So so you are given a root of a binary search tree BST and an integer val. So find the node in the BS binary search tree that the node value equal val, and return the subtree rooted with the node. If such node does not exist, return null. So let's move this. Good now. Hey, welcome stream. So we have a binary search tree, and we have the value. We have two input, which is the binary search tree itself and the value. The value is 2. Then we're gonna return the binary tree which root equal to 2. Okay, and here the value, we didn't find the value, so we're gonna return a empty root or a empty list. Okay, so let's break this problem to small parts. Let's copy this here. Okay, so mainly in the binary search tree, or in the tree generally, we use recursivity. So I think here also we're gonna search using recursivity, but the thing with the binary search tree, that it has some properties, which are the number on the left of the node is smaller, and the number of situated in the right is greater than the node. So to find the value, which is here value equal to, if the value is smaller than the root, then we're gonna go left. If it's not, we're gonna go right. So I think this shouldn't be easy. Okay, so let's go to the problems. So I don't need that anymore. And okay, don't really see it. Okay, let's look at this. So here we're gonna begin with the condition if there is no root. So if not root, then return, gonna simply return nothing. Else, so if the value is smaller than the root dot var, then we're gonna go. Okay, so let's put the condition and then val is greater than root, and there is the final condition, which is when we found the key itself. So if the key is the values, then we're gonna simply return it. So we're gonna return root. Okay, so so here we're gonna go left. We're gonna go right actually. So self dot search bst of root dot right, and here the value, and I'm gonna do the same thing with the left. Simply gonna make it left. But I think we have to return this value. Okay, so let's just run it. Okay, so it's correct. Okay, so on every time I want to print the root. Okay, so I'm gonna make it here. Print root dot flash. I think we have, every time we go the right or the left, you have to change the. Okay, so what is going on here? Invalid syntax. Oh, okay, so so I'm gonna make it here. Okay, so I'm gonna make all this if, and here to make it, to clarify it, so equal root dot val. Okay, and here I'm gonna print it to see what is going on. Okay, so here the value is 4 and then 7. Okay, so I think here we have to make root equal root equal. Oh, so eval so we have to return this. Just can return the root. Root equal, or do we have to change? Okay, so self okay, so root equal root dot if we make it here, so here will be root dot right dot right. Okay, so simply gonna go to root, and here root equal root dot left. Okay, so why is that? I'm gonna make this back, this dot left, and see. Okay, so 4, 2, and 1. Eval equal. Hey, hello, man. Welcome stream. So if eval I'm gonna make it if thing here enough and here else. Okay, so here we're good. Okay, so I just want to print every time. Okay, so now he's returning a empty list. Why is he returning an empty list? An empty note. Okay. Same thing. Okay, let's go. Root equal and root equal. Hey, thank you, man. Thank you. Welcome stream. Okay, so he's still. So root equal. Can I print all this? Can't I? If not root, then return nothing else. Return root. What is going on here? This should be easy. I don't understand why this is not working. So I want to check. Okay, so print root. Okay, so let's print root. Okay, so 4, and then 2, and then 1, and then 3. 3 node 7, 1. Okay, I'm gonna make elif var equal equal dot dot var. Okay, so 4 and 7. And then why he, so, and then, so he did find it, return root. So the root is 4 and then the root is 7. Level, oh, so root level, okay, so I'm gonna print rooted val here. Why is not, so 4 2, why, so, okay, I'm gonna just print find it to check if he is entering this condition or not. Okay. Oh, I get it. So he's going. Okay, so if val is so rooted val is 4. So it's gonna go right. Okay, so I just switch it. I don't think this gonna work, but okay, so 4 and 2 and then find it. But why didn't he return it? Okay, so 4 and 2. Okay, so he found it. He found it. Find it. If the value is this, should not go on the left. Hey, yeah, thank you. So find it 3 node 2 1 3. Why isn't he? So okay, so I printed this and then I return it root. Why the output is why the output is like this? Return root. Does he? Oh, I think not. Oh, this is it. So the return should be here. Can't. So I think I can erase all this. Okay, let's test it like this. Okay, so it's good. Now we're submitting. Okay, so we're good. Like I told you, this should be easy. So 3.dfs sample. So if root return else return root. Okay. So first problem in like 20 minutes. Oh, it's too long for a problem like that, honestly. But yeah. Okay, so the second one is the delete node in a BST, and that for homes carefully remove false lead from the case while keeping the investigation intact. So given a root node reference of a BST and the key, delete the node with the given key in the BST, retain the root node reference, possibly updated of the BST. Basically the deletion can be divided into 2-stage search for a node to remove. If the node is found, delete the node. Okay, so we're gonna search it first and then delete it. So this, and we're gonna delete 3. So v4 will have the place of 3. So 2. Oh, so we can either replace it by 2 or by 4. Okay. Okay, I will choose to replace it by 4. Okay. Okay. It can be either 542 or 524. Okay. Okay, so let's get this. And let's go. So we don't need that. So basically, the problem will be divided into two. The first part is searching for the key or the node we're gonna delete, and then deleting it. So the first part is pretty easy, like the previous problem. Simply gonna search in a like the normal binary search tree, and then we're gonna do so the delete. He said we either replace it by 4 or by 2. Okay. Okay, so this is the case if we have 2 children, but if we don't have children's, so we're just gonna delete it. Okay, so let's write this. If we have, so the first, if we have no child, then simply delete it. Excuse my my hand drawing. And okay, so if we have so if we have one children, we're gonna simply one child, so we're gonna simply replace it by it. And third, if we have 2 children, then we're gonna choose. Okay, so we're gonna choose. And if it has 2 children, okay, so let's start for the first part, for the search part. So the search part is very simple. So like usual, if not root, so we're gonna return if key is greater than the root dot val, then we're gonna go right. So we're gonna just simply make root equal are we gonna make root dot right or root? Okay, so let's start with root equal. Okay, okay. So let's visualize it. So if we have 5 and 4 and 7, and the key is 7, so we're gonna delete this. So I'm gonna go right, and what we are going to return. So okay, I'm gonna return the actual binary tree, so not the root. I think so. Root dot right. Okay, okay. Equal delete node of root dot right, and of course we don't forget the key. Okay, so we're gonna repeat this with the with the key is lower, then I'm gonna make it dot left, and this is dot left. Okay, and then we go to the else. I'm gonna go to the else or to make it more. So key equal root dot bar. So what you're gonna do? Okay, so we have 3 cases. If the node doesn't have children, so like this, we're simply gonna delete it. So if not root dot left, so if it doesn't have left, so simply gonna go right. So if it doesn't have this left, so we're gonna go right. We're gonna place it with it, so this wouldn't be 3, so it will be 4, and then we have to delete this. And if it doesn't have the left children, so we're gonna replace it by the 2, and we're gonna delete the 2. Okay. So let's make that into code. Okay, so if not root dot left, we're simply gonna go right. So root equal root dot right. Root equal root dot right. No, we're gonna return it actually. Yeah, we'll have to return it. So simply return it. And the other case. So if not root dot right, so I'm gonna make root dot left. So this is the case that it has 1 child. And if it's not, we're simply gonna if it's this is it. But imagine that we have a tree that is like, okay, so let's put this here. Okay, so imagine that the tree is going up. So like this 4, so like this will be 2, and this is like 5, or we don't really care, but we have to go to the minimal, or we cannot go to the 5 actually, or we cannot go to the 8. Let's suppose we have 8, so we cannot go to the 8 and replace the 8 with the 3 and then delete the 8. So we have to replace it with like a number that is lower than 4, or lower than 3. So we're gonna replace it with like 3 or 2, or okay. Okay, so I'm gonna make, I think, a variable. Current left. Or something, gonna make a root left. Okay, what we're gonna do? So after all this, okay, so after all this, we're gonna simply return. Let's keep it in mind like this. So we're gonna return root. Okay. Can we try this to see what happens? Oh, self. Okay. Self. And it is self. Already. So I think this is good. And okay, so 5 3 6, and then 2 4, and then null, and then 7. So what did he replaced? 5, oh, so key is 0. Oh, so he didn't find the key. Oh, so if the key is not found and the node is empty, yeah, probably he will not, he will return. So but here, okay, so like we have 5 3 5 3 6 and 2 4 7, and here we have 5 4 7 null null. So he replaced the 4 with the 3 and make the null. Okay, so I think we have one more thing. Okay, so I think I'm gonna make a current. Gonna make a variable current equal. I'm gonna go right, so I'm gonna make current dot right to get the minimum, and then I'm gonna make a. So we're gonna go through the binary tree. So I think this is the best way to make a while current. While current will take current dot left. Dot current, take current dot left. Oh, so okay. Does this change anything? Okay, so 536. It doesn't do anything, so because we have to delete it. We didn't delete it yet. So while okay, so let's just delete it. Okay, so we're gonna make root dot right equal dot right equal self dot delete node. Okay, so I'm gonna make this. I'm gonna delete the current or dot right. With the key. The key, yeah. So it didn't do anything. If this is medium, I don't want to see hard. So yeah, it's not more complex example will really come in handy. Okay, so it's bullshit honestly. To solve it, you need to look into crystal ball like fortune teller. Man, the comments are crazy. Okay, let's go back. So the thing is, I think this current dot left to assume that it's a current, and then we simply have to. Hey K, hello, how are you? How's your day? And we have to make the root dot val have the current dot val. And then we make the root dot val, which is the current dot val. Like you're all the same. Can we run it? Let's see. Oh, we're good. Yo, so when did we solve this problem? Like, okay, so when did we start it? Like 20 minutes? Okay, so we have been on this problem 20 minutes. Yeah. Yeah, now it's 40 minutes. We did 2 problem minutes. Let's play this sub. Oh, man, we did it from like the second or the third attempt, and it's like 20 minutes. Yeah, and the others say it's pretty hard. Oh man. Yeah, so I think I'm good in the binary tree search. Yeah, I suck in the DFS and the BFS, but in binary tree search, it's not the. Okay, there could be multiple ways of. Delete two. I can have one. Went wrong in this case with the input only. Should be both root and key. Okay. So let's find min. Okay, so he's gonna find the minimum. I chose to go up, go down left to the minimum to the last left node. So I found the minimum, and he chose to. Oh yeah, he did it too. He defined a function here which finds the minimum, which is the node dot left. He went down to the last left node, and he found the minimal value. Okay, so I think it's a record. We did two problems in 42 minutes, and one of them was not pretty medium. It's between medium and hard. Honestly, I don't know what to do now, so we did those two. We did those two, and then graphs. Well, I think I did this with my friend last month, but now I think I'm not gonna be able to solve it. So let's just discover it. So graphs. Okay, I have a pretty good video about it, so let's go. It is a good opportunity to show to you. So 15 code patterns. So this guy is pretty. I think the sound is cool. Okay, so let's. Okay, let's go.
Code problems. If there is one thing.
So in this video, this guy is talking about the patterns of solving the lead code problem. So you don't have to solve it randomly. So he's talking now about the arrays. So he talked about the arrays.
The sum of all elements.
And then,
formula.
About the prefix sum. The prefix sum is a good pattern to sum the array. And this the two pointers pattern. This sliding window pattern is a interesting pattern. Okay, and then this the two pointer in a linked list. The slow and the fast one. So to check if there is a loop in the linked list, or to delete a node in a linked list. This to reverse the linked list. This to find the top k element or the lowest k element. This the heap and to k element. I think he talked about the graphs. So here we have a okay. So now we have the binary search tree or the binary tree. He's talking about DFS now, and then he's talking about the BFS. I think now he's gonna
graph. Printing all nodes of a tree level by level. Finding all connected components in a graph. Finding the sorted transformation sequence from one word to another. To implement BFS, we can use a queue, visited set or array to track process nodes. Continue while the queue is not empty. It set is the matrix traversal pattern.
Okay, most so there is no graph. Okay.
Traversal problems can be seen as graph problems. In a graph, you have nodes and edges. In a matrix, which is usually a 2D array, Your nodes are the cells from where you can reach to adjacent cells horizontally, vertically, or diagonally, depending on the problem. Depth-first search, or DFS. It is used to explore all paths or branches in graphs or trees to solve problems like finding a path between two nodes, checking if a graph contains a cycle, finding the topological order in a directed acyclic graph, and counting the number of connected components in a graph. DFS can be implemented recursively or
honestly, I don't know
using a
much
stack.
of a
Here
thing
is a generic approach
about the graph, so I'm simply gonna search it. So Graph-dfs. Okay, so I think this is very popular, but it is very long. So okay, the first search. So let's look at this.
Nutty.
So you can consider it as a study with me session.
My name is William, and today we're moving on to talking about the depth-first search algorithm, which plays a central role in several graph theory algorithms. So what is a depth-first search? A depth-first search is a core algorithm in graph theory that allows you to explore nodes and edges of a graph. So it's a form of traversal algorithm. The nice thing about a depth-first search is that it's really easy to code, and it runs in a time complexity of big O of V plus E, that is vertices plus edges, which is directly proportional to the size of your graph. By itself, a depth-first search isn't all that useful, but when augmented to perform other tasks, such as count connected components, determine connectivity between nodes, or find bridges and articulation points, the depth-first search algorithm really shines. So let's look at an example. As the name suggests, a depth-first search plunges depth first into a graph without regard for which edge it selects next, until it cannot go any further, at which point it backtracks and continues its exploration. So a depth-first search has to start on a node, and I'm going to start our depth-first search on node 0, and now we arbitrarily pick a node to go to. So from node 0 we're going to go to node 9, then from node 9 we only have one choice, which is to go to node 8. At node 8 arbitrarily pick an edge, so we're going to go outwards to node 7. Node 7 we have plenty of edges to choose from, so let's go to node 10 to node 11, and 11 to 7. So we don't want to revisit already visited nodes or nodes that are currently being visited, so we have to backtrack. To indicate backtracking, I'm going to label edges and nodes as gray, so backtrack all the way back to node 7.
So this what about? So the graph, we have to iterate through the graph, and we cannot revisit the node, and if we visit it, we're gonna use the backtrack. Okay.
We're not finished exploring node 7 because there are still edges to be picked. So I'm going to go to node 3. At node 3, I'm going to go to node 2. Node 2 is a dead end, so we backtrack, then go to node 4. Node 4 is also a dead end, so backtrack from node 4 back to node 3, then pick node 3's last edge to go to node 5, 5 to 6, and 6 to 7. Can't go to 7 because we're visiting 7 currently, so backtrack all the way back to node 8. From node 8, we still need to visit its last edge, which goes to node 1. Node 1 back to node 0. We can't go to node 0 because we're currently exploring it. Then backtrack all the way to 0, which completes our depth-first search traversal of this graph. So this was one particular depth-first search traversal, but as you saw, it could have gone a lot of different ways. So now let's look at some pseudocode for this depth-first search to get a deeper understanding of how it works.
Okay, so from the first look of the code, so we have n, which is number of nodes in the graph. Can we count it from the beginning? Okay, so G equal adjacency list representing graph visited. Oh, so we're gonna initialize a list. It is initialized. Its length is n, which is the size of the graph, and then we're gonna initialize all its value to false. Okay, then we're gonna make the function dfs at which is the root, if visited at, oh okay, yeah, which is the next node, then return visited, oh okay, if visited, then we're gonna make it true, and neighbors equal graph add, which are the next node. For next in neighbors, oh, so we're gonna make a for loop and a recursivity. Okay, interesting.
The first thing we'll need to do is initialize these three variables, which are n, the number of nodes in our graph, g, the adjacency list representing the graph, and visited, a Boolean array containing true or false at index I depending on whether or not node I has been visited. In the beginning, this array should have all false values because we have not visited any nodes in the graph. Once that is set up, at the bottom I define our starting node to be node 0 and then call the depth first search method to do the exploration.
Oh, okay.
The depth first search itself has one argument, the current node we are at, which I have conveniently named at. This method is recursive, so I check the base case, which is whether we have already visited this node. If so, we have no business here and can return. Otherwise, let's visit this node by marking it as true and exploring all of its neighbors. To explore all the neighbors of the node, reach into the adjacency list and pull out all the neighbors of this node and explore them depth first by looping over each and recursively calling the depth first search method. And
why don't we just type dfs of next? Why we have to graph of at? Okay.
That's all a depth.
So it's not really like the dfs of a binary tree. So just we have to add the for. We have to initialize the neighbor and then loop through it.
First search really is in a nutshell. Let's look at another simple use case for a depth first search. I want to discuss finding connected components in a graph. First, let's understand what we mean by connected component. Sometimes a graph is split into multiple disjoint components, and it's useful to be able to identify and count these components. One way to identify these components might be to color them so we can tell them apart. But what does coloring nodes really mean to a computer? Coloring nodes is equivalent to labeling each node in a component with the same ID value. For example, every node in the purple component gets an ID of 1, and every node in the green component gets an ID of 3.
Have you tried contributing to any?
We can use the depth first search to...
Yeah, so I have this problem which is contributing to any open source project. I really don't have the experience. I saw it in the internet, but I didn't have the courage because I have other project related to my uni. So I didn't really try it, but I'm considering trying it in the next, in the upcoming period actually. Welcome to stream, by the way.
To identify components this way.
But beside the open source project, I did a project on my own, but I really consider doing or contributing to open source project.
Let's make sure all the nodes are labeled from 0 to n non-inclusive, where n is the number of nodes. The basic algorithm is to start a depth-first search at every node, except if that node has already been visited, and mark all reachable nodes as being part of the same component using the same ID. So if we start at node 0, then we do a depth-first search here, and then every node in this component gets an ID of 0. So we go to 8, given it an ID of 0. 14 gets 0. 13, also label it with a 0, then backtrack like you do a depth-first search, then explore node 4, give it an ID of 0. And then finish exploring that component, and then move on to the next node in order, so go to node 1 next. Then node 1, start a depth-first search there, so go to node 5, the 1, backtrack, go to 16, also label it with a 1. We're finished exploring this component. Then we would go on to node 2, wherever node 2 is, then explore that component. Then node 3, explore node 3 for every component, unless node 3 has already been visited. And we used a depth-first search to do that. Awesome, so that's how we find connected components using a depth-first search. Now let's look at some pseudocode for how we do this. First, we'll need a couple of things. We'll need everything from the previous code we looked at, so n, the number of nodes in our graph, g, our adjacency list, and our visited array.
Yeah.
But additionally, we'll also need a variable called count that tracks the number of connected components, and components, an integer array that holds the integer value of which component a node belongs to. Inside the findComponents method, we loop over every node and check if the current node has been visited or not, and then execute some logic. This depth-first search variant differs slightly from the previous in that we execute a depth-first search for every unvisited node. When we actually do the depth-first search, we visit nodes and mark them as visited. So we never revisit the same node more than once. We either skip over a node because it's been visited in this for loop, or start a depth-first search there. If we start a new depth-first search, we increment the count variable and keep track of how many depth-first searches we have done. Inside the depth-first search method itself, the two things we do are mark the current node as visited and set the current node to be part of the component equal to the value of count. And then simply iterate over every neighboring node that has not yet been visited.
So the logic behind it, if we find if the node is visited, it's already visited, then we're gonna skip this if condition, and we're gonna go to the next iteration. And if it's not visited, then we're gonna count and we're gonna increase the count to make it like the first group is of node R1 and the second R2, and then we're gonna apply the DFS. The DFS is gonna make the visited node true, so we visited this node, and the components, which is this array, we're gonna make at it count.
Visited, and call the depth-first search method to explore them as well. Back inside the findComponents method, simply return the number of components and the components array that contains the information about which component each node belongs to.
Okay.
So we've covered two of the things you can use a depth-first search for, doing a simple traversal and determining connected components. But we can augment a depth-first search to do so much more, such as compute a graph's minimum spanning tree, detect and find cycles in a graph, check if a graph is bipartite, find strongly connected components, topologically sort your graph.
So we have a lot of problem to work on it on a DFS graph, including those. And tomorrow we're gonna work on those. So, like I said, I did this in the last month with a friend of mine that I know him on this stream. So I think Python. What is my or Java? Okay, so I did it in Java. Interesting. So we did this is about keys and room. I remember it. So in every there is a list of rooms in every room. So every room is a list, and in this list there is a key to the other room. So this room, if we visit this room, so we have the key to the index, to the element which index is 1 and which index is 3. So we can go here and here, and if we go here, so we're gonna 3, which is this number. And if we go to the if we visited all the rooms, then we're gonna return true, and if we're not, so we're gonna return false. So I think we here, so we did a for loop to know if we visited this room and not, and we used a stack. So where's synchronity, current pop, we're gonna pop every visited room, and then visited current, we're gonna make it to true. Then we used neighbors. Okay. So yeah, so I think he watched the video, and honestly I didn't watch it back then, and he did this solution. He's very genius man. And then another one. Till now I don't understand this. So for volume visited, oh, so this is to check if the all rooms are visited or not. So if it's not, we're gonna return false, and if it's we're gonna return true. Yeah, very clever. So as I said, tomorrow we're gonna work on those problem. Revise the Graph-dfs, revise it to work on it tomorrow. I think now it's 1 hour 2 minutes. I think this is the end of stream. I hope that this video or the stream is good. Hope you liked it. Thank you everyone for watching. Thank you everyone for subscribing. Now we are nearly 550 followers. This is really good, and this is really amazing, man. I hope you like this video, and as usual, see you tomorrow. Good night.